This is the screencast for section 10.2, example 8, displacement versus distance traveled. Well, you have a grasp of what displacement means. Now in vector form, that's still going to be the straight distance between 2 points, but we're going to separate that into the horizontal distance versus the vertical distance. So we have the horizontal distance and then vertical distance that gets us from the point where t equals a to the point where t equals b. So instead of following the path, we can just use displacement to find where that new point is. Now if we want to calculate the total distance traveled along every little piece of that path, we're going to have to use arc length, and we'll use the arc length formula from section 10.1, but now it's adjusted to vector form. So basically you have v sub 1 of t, which is, if you remember, the x parameter prime squared, plus then the v sub 2, which is the y parameter prime, or the derivative, squared. That's going to calculate the entire arc length if that particle followed the whole path between the point where t equals a and the point where t equals b. So in example 8, we're going to find the displacement and the distance traveled. A particle moved in the plane with velocity vector v of t equals, well, that mess, at t equals 0. The particle is at the point 1, 5. So that's where the particle is at now. We want to find the position of the particle at t equals 4. The position of the particle. So we're going to use displacement for position because all I need to know is the new location of this point at a new time. I don't need to know how far it traveled or anything like that. I just need to know the position. So I'm going to use displacement, which means I'm going to start to set up the formula. Those antiderivatives are both going to go from 0 to 4 because we started at t equals 0 and I want the position of the particle at t equals 4. v1, or the horizontal expression for velocity, is t minus 3 pi cosine of pi t. And then the vertical expression for velocity, or v2, is 2t minus pi sine of pi t. So if I integrate that, I get 8, 16. Now, the point started at 1, 5. So let's say it followed this weird little path here, and there's 1, 5. All we want to know, we don't need to know anything between t equals 0 and t equals 4. We just want to know what happens to jump from t equals 0 to t equals 4 to get us to our new point. Well, I know that this particle traveled a horizontal distance of 8 and a vertical distance of 16, so 8 and 16. So yeah, there might have been some weird curly cues in the path here, but basically what happened was it moved right 8 and up 16 from 1, 5. So that means at t equals 4, the particle will be at 8 plus 1, 16 plus 5, which is 9, 21. So that's the location of the point at t equals 4. Now, what was that total distance traveled by the particle? Well, I'm going to use the arc length formula for that. Again, integrating from 0 to 4. The horizontal parameter for velocity stays the same, t minus 3 pi cosine pi of t, and then square it, plus the vertical parameter of velocity, 2t minus pi sine pi t, and then also squared, square root of the sum of those. I get 33.533 units, which means then if this particle was on the same path, it still goes from 1, 5 to 921, but it travels this 33.5 unit long path in between those 2 points. In part A, the particle still traveled along that path. We just didn't need to know anything about the path. We just wanted the ending point. That's how we were able to use displacement. The now try problem number 37 says the velocity v of t of a particle moving in the plane is given, along with the position of the particle at time t equals 0. Find A, the position of the particle at time t equals 3, and B, the distance the particle travels from t equals 0 to t equals 3. Alright, so let's start out with part A. The position of the particle can be found just using displacement. I only need to know its location. I don't need to know anything about the path to get there, just its location. So the new position is going to be the displacement going from point 2, 6. To calculate the displacement, I'm going to find the antiderivative of the horizontal velocity parameter But again, I'm starting from 2 comma 6, so I could just add 2 to that because I'm going to go 2 plus whatever the displacement was. Same with vertical. I'll do the vertical parameter from 0 to t. Now t is going to be 3. I'll do that in the next step. But then I'm adding the original y location, the original height of the first point at t equals 0. So now when I take the antiderivative, I'm taking the antiderivative from 0 to 3, the new time, the point at this new time, t equals 3. So here's the displacement plus the initial value of 2. And then here's the vertical displacement plus the initial vertical position of 6. That means I get 18 plus 2, comma 3 plus 6. So the displacement was 18, comma 3, but I'm going from the point 2, comma 6 to get me my new location of 20, comma 9. So at t equals 3, the particle is going to be located at 20, comma 9. Part B, the distance the particle traveled. Well, that's going to be arc length formula, so I use the horizontal parameter and vertical parameter from 0 to 3 times 0 to 3, and I get 19.343 units.